Hello, everyone, and welcome back to Nunley Math. I'm your host, Aaron Nunley. Thank you so much for joining us here today as we wrap up our discussion of surface area. If you've been following along with us, you'll know that we spent a day introducing the idea of surface area and how it refers to the what it takes to cover the outside surfaces or exposed surfaces on a three-dimensional object. We also, that day, talked about how you calculate the surface area of a rectangular prism. We followed that up with a day of discussion about how to find the surface area of a triangular prism, how to find the surface area of a cylinder. So that brings us to the last of the shapes we're going to look at, and that is the surface area of pyramids. Now it should go a little faster for us here today because we already understand that the surface area of a figure is just the exposed surfaces. So when I get to a pyramid, what I have to do is realize what types of surfaces I need to be looking for. A pyramid is defined as a polyhedron composed of a single polygon base. Remember that our prisms had two polygon bases with all the sides connected to triangles that meet at an apex. Prisms had two bases and all the other sides were rectangles. Pyramids have a single base and all the other sides are triangles. So if I were to give you this figure, this is a square pyramid. Notice that the bottom is a square and it is composed of that square plus 4 additional triangles. It's a little hard to see when it's in 3D form like that, so we could also look at the net of that figure. If you unfold it, it's going to have a square in the center and it's going to have 4 triangles along the outside edge. You have triangular pyramids. Notice that the base is now a triangle and each side of that triangle has another triangle or an additional triangle attached to it. Unfolded, it looks a little bit more like this. And then lastly, we just want to keep in mind that no matter what polygon we have as our base, we just attach whatever number of sides it has, that number of triangles to make our pyramid. So this happens to be a hexagonal base, which makes it a hexagonal pyramid, which means it has 6 sides on the base or 6 triangles along the side. If I unfold it, it's going to look something a little bit more like this. Now I know it's sometimes difficult to see the relationship between a net of a figure or the figure unfolded and the three-dimensional figure itself. So I'm going to hop out of this program into an application that I got from shapes.learnteachexplore.com called Shapes. And we'll look at how those images are related to one another. It's going to be almost like magic. You ready? Here we go. So we are now inside of the Shapes application. You'll notice that there are lots of different figures we can look at. I'm actually going to click on pyramids and I'm going to grab this quadrilateral pyramid right here. Notice that the base is a quadrilateral. It's a 4-sided figure. This one also happens to be a square, so we could also refer to this more specifically as a square pyramid. I've colored that green for you. Notice the square has 4 sides. When I look at the other sides or the other faces of this square pyramid, you'll notice that all the other faces happen to be triangles. And in fact, if I come over here to the far right and grab my unfolding tool, you can see how that square pyramid can be unfolded into a square with 4 triangles. Now, I could come over here onto the Nets button and I can actually click and show different ways that that can be unfolded so that all the pieces are attached in different locations, but this tends to be the most common net that we see. Let me fold that back up for you so you can kind of see. And there you go. I'm going to hop out of here. Let's look at the triangular pyramid. This is a triangular pyramid. It's also often referred to as a tetrahedron. We do have a triangular base. And when I unfold that triangular figure, you'll notice that this also folds into a flat shape. Notice you have your one base and you have your 3 triangles. Now, this is not the most common net that we tend to have for a tetrahedron. This one tends to be a little bit more like that. I'm going to fold that back up for you. And there you go. I thought there might be a third net in here, but I'm not seeing it. And that's quite all right. The important thing is to realize a triangular base means there's going to be 3 additional triangles. And I can go through here and I can grab a bunch of different ones. Here's that hexagonal pyramid we were talking about. Notice that the bottom is indeed a hexagon right there. And if I were to unfold this, you can see that there are 1, 2, 3, 4, 5, 6 different triangles. Again, that is not the most common one. There it is. That's what I want to see. This one's a little more common. And you can see how those triangles fold up, and they all meet up here at the apex. I'll unfold that one more time. Okay. So that's really the key characteristic for pyramids. When I'm trying to distinguish between pyramids and prisms, I count the number of bases, and then I look for all the other sides. One base, all the other sides are triangles, that makes a pyramid. Two congruent parallel bases, and all the other sides are rectangles, makes it into a prism. We're going to hop out of this app program back into our PowerPoint. It's going to be just like magic. Here we go. So we're back inside of our surface area PowerPoint. One more thing I do want to point out. You'll notice that when you have a pyramid, you actually have two different heights. When we talked about prisms, we mentioned that the height of the prism helped us with calculating the area of the side faces. But we need to keep in mind that a pyramid actually has a regular height, a height between the base and the apex, but then you also have something that's referred to as the slant height of the figure. Notice that the slant height is the height of the triangle along the side. Now, if you remember from the Pythagorean Theorem, if you were to make a triangle here from the slant height to the center and measure up the height, this third side or hypotenuse is actually always going to be longer than the actual height. So you want to be clear when you're trying to find the area of all the surfaces about the fact that if you want the area of this triangle, you have to use the slant height, not the actual height. Now, just like we've done before, when I see the shape, I do know this is going to be one square and four triangles. One square and four triangles. So when I ask you to find the surface area, I'm asking you how many inch squares it takes to cover the entire pyramid. Or what is the surface area of the square pyramid? So I'm going to make a table just like I did before. Notice that this time I have a square, which is length times width, and I have four triangles. When you look at the base here, since the base is a square, that means all the triangles are going to have the same size base. And in most cases, the pyramids that we work with at least, are all going to have the exact same height. There's a couple instances where that doesn't happen. We can talk about those when we reach them. Okay, so let's go ahead and do the area of the square. I can see it's a 16 by 16, so it has an area of 256. We remember that the formula for the area of a triangle is 1/2 base times height. The base of my triangle is 16. The height of my triangle is 17. Remember, that's the height of the triangle, not the height of the pyramid. I plug in those values, and you get an area of 136. Fortunately for us, these are all going to be the same size triangles. So I can just duplicate that value without having to write anything else. And I add them all up and get 800. Now, let's come on over here. Remember in our other videos on surface area, we did say you could do this in formula form. So instead of making the table, you could just say, well, I'm doing a square plus a triangle, 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 triangle. Or the area of the square is 16 times 16. And then I have four triangles that all use the same formula. Do a little computation, you come up with 800 centimeters squared. Shouldn't be that bad, right? Let me hide this from us. There we go. Shouldn't be that bad for you. Here's what I'm going to recommend. This next slide is going to be just examples of the exact same thing. I want you to try the first one on your own. Pause the video to do that and then restart the video. I will do it a little more quickly. And then I want to talk with you about these other two. They do have some slight variations you are going to want to be aware of. So try that first one real quick. If you feel pretty comfortable, you can skim through my explanation, jump right to the solution. Remember, we're looking for the total area of all the surfaces. Because this is a square pyramid, I have the square base and four triangles. The base is an 8 by 8, so it has an area of 64. The triangles are all 8 wide and 10 tall. Remember, that's the height of the triangle, which is longer than the height of the pyramid. Or you get an area of 40. There's four of them, they're all the same. You get an area of 224, or a surface area of 224 square inches. And just like before, I can also do that in formula form, where I plug in those values, and I get the same thing. Now this middle example is slightly different. Notice that the base is not a square. The base is a rectangle. What that's going to do, number one, is it's going to change the triangles so they're not all the same. Because this is a rectangle, if this base is 5, this one is also going to be 5. Because this side or this width is 8, this width is also going to be 8. So when I go to plug in my numbers, the area of the rectangle is still pretty easy. But when I go to do my area of my triangles, I have to keep in mind that these two sides, this one here and the one back here on the back, are going to have different areas than this one here on the right and this one back here on the left. Well, one of them, the one over here on the right, is 5 for the base, 8 for the height, which gives you an area of 1/2 of 5 times 8, which is 20. And we can just duplicate that back here on the back. The front is 8 by 6, which gives you an area of 24. The back is going to match. You add them all together, and there's your surface area. Or you could do it in formula form, just like we've done before. Add all the areas, or you could say, well, I have 2 that are 20 and 2 that are 24, plus that base of 40. Either way, your solution can come out the same. Now, this is the one that gives people some difficulty. Notice that the bases are not indicated to be congruent, but we're going to go ahead and say that all the sides of the base are congruent. So this is going to be a 16 by 16 square. We're looking at a square pyramid. However, there are some things about this that make this a little more difficult. Can you spot those? Well, it's still a square and 4 triangles, but after I find the area of the square, I want to find the area of the triangle. This has a base of 16, but take a look here. I actually don't know the height of my triangle. I know the base is 16, but I don't know the height of the triangle. I can tell you the height of the pyramid is 24, but I can't tell you the height of the triangle. And without that measurement, there's no way for me to calculate the area of that triangle. Now, you might be able to look at this and recognize something that might help you with finding the height of the triangle. I'm going to pause for just a second and let you think about that. I'm going to assume if you wanted more time that you went ahead and paused the video to do that. Hopefully you recognize that if the height of the pyramid is 24, you can actually find the base of this triangle by realizing the height goes from the center to the edge. If the edge is 16, the distance from the center to the edge must be 8. And once I know that, I have 2 sides of a right triangle. How do we find the missing side of a right triangle if we know 2 of the sides? Well, that's the Pythagorean Theorem. So I know 1/2, I know the base, I need to find how long that last side is or what the height is. We call that the slant height, and we're going to plug values into Pythagorean Theorem. A squared plus b squared equals c squared. Now, we already said the distance from the center to the edge is 8. This side is 24, so we plug those values in, do a little computation. How do I undo squares? Well, I square root both sides. When I square root both sides, I get c is the square root of 640, which is about 25.3. In my class, we're always going to round this to the nearest tenth. That ensures that we're all getting the same answers when we go to work this out. So I'm going to plug in that 25.3 for the slant height. I'm going to do my computation, and I'm going to get 202.4. Since the base is a square, I know those are all the same. And when I add them up, I get a surface area of 1065.6 square units. Notice I wasn't given units in the problem, so I just said square units instead of square inches, square centimeters, or anything like that. And there again, just like before, I'm just going to plug in the values. You can use the shortcut if you want, and then you let your calculator perform the computations. Remember, in my class, you should either make the table or you should do the computations. You are not required to do both. If you have to use the Pythagorean theorem, you would be required to show that work as well on your paper. Here's an interesting one. This is a triangular pyramid or a tetrahedron. Notice that your base is a triangle and that all the other sides are also triangles. Now it's important to note that this is an equilateral triangle, meaning that all sides on this base triangle are 8. That's a good indication for us that all the side triangles or all the lateral facing triangles are going to have the same area. So when I go to set this up, I know I'm going to have to use 1/2 base times height to get the base here, and I'm going to have to use 1/2 base times height for all the other sides. You can't assume that all the sides have the same area. So here's what I'm going to do. Notice my base is an 8 by 8 by 8. I went ahead and redrew that. How do we find the area of a triangle? Well, 1/2 base times height. I know my base is 8, but I don't know the height of the triangle. I can indicate it this way. Does that help? Well, here's a thought. If I create the height or put the height in, you can see that I can take that large equilateral triangle and I can split it into 2 right triangles. And when I split into 2 right triangles, each half of this side is going to be each side of this triangle is going to be congruent. They're both going to be 4s, which means I now know that this side is a 4, this side is an 8. I should be able to calculate that third side. Do you remember the formula for that? Well, that's the Pythagorean Theorem. Notice that this time, I know one of the legs is 4. I also know the hypotenuse is 8. Remember, the hypotenuse is the longest side. It's across from the largest angle, the 90-degree angle. And once again, I can use my Pythagorean theorem to compute that the height of this triangle is going to be 6.9. So I plug that in. Once again, keep in mind, I've rounded to the nearest 10th. Students in my class should always round to the nearest 10th on these. That way we all get the same answers. And we can compute that. Fortunately, that's the hardest part of the problem, because the other triangles are all bases of 8 and heights of 12. Which makes them all 48s for a surface area of 171.6 meters squared. And once again, you can either do it in the table or you can do it using the formula mode or formula form, 171.6 meters squared. One last thing, I can give you pyramids of any shape. There are some sophisticated geometry ways to calculate the area of a pentagon. However, at this point, I am not requiring that my students can do that. Instead, if I gave you one like this, you would just need to realize that this means the area of the base is 43 inches squared. That means that I've already given you the area of the pentagon. All you need is the area of the triangles. And notice this is a regular pentagon, meaning that all the sides are the same. That's going to make all the triangles the same size as well. So I'm going to have a pentagon and 5 congruent triangles. Or I'm going to be given the area of the pentagon, and I'm going to compute the area of one of the triangles and multiply it by 5. Again, from there, it's computation. Hopefully that wasn't too quick for you. Certainly when we have to find the missing heights using the Pythagorean theorem or find slant heights using the Pythagorean theorem, it is a little more challenging, a little more complicated, but it really is just a matter of slowing down, making sure we show our work, and making sure that we don't make any small calculation errors. Our next lesson is going to be dealing with the volume of prisms and pyramids and cylinders and cones and those kinds of things, so we're looking forward to that. As always, thank you so much for taking the time to join us here today. Please leave us a comment in the comment section so we know you're there. Make sure you smash that like button. Make sure you ring that bell to turn on notifications so that you know what's happening here at Nunley Math. You guys take care of yourselves, all right? Bye-bye.